This section deals with the rational canonical form of a linear transmission T in f of A of V. If in the case of Jordan form of linear transmission, T must have all of its characteristic roots in F, but in rational canonical form, the location of characteristic roots is not assumed. Now, to prove the main theorem, first of all, we see that our V is a vector space over a field. In fact, it's a finite dimensional vector space, and it is also given another structure, namely fx module. We are going to make this V an R module, where R here is fx, and we know pretty well that our fx is a Euclidean ring. It's a Euclidean ring. So we are going to make our V as an fx module. Already we know that V is a finite dimensional vector space. It's a finite dimensional vector space. Throughout the section, we is assumed to be finite dimensional vector space. Now that we are going to give a module structure, already it has got a structure vector space. Now we are going to give a module structure to this. So if we need to have a module, then we need to talk about a ring also. So that ring is taken as the ring of polynomials, namely fx, and that is known to be a Euclidean ring. So for this we need to have, see, already V has got an operation addition, under which it is an abelian group, and we need to have one more operation in order to make this to be a module, and here module over fx. So for that, what we need to do is we have to consider an element from fx, and an element from V, and the resultant should again be a member of V only. So how that is described? So you consider small v in capital V, and you consider f of x in fx, and define this multiplication. In the case of vector space, we call that multiplication to be scalar multiplication. For convenience sake, we may call here that as also scalar multiplication. So here it is an fx module. There is no actually name given to this, but we shall, for convenience sake, we shall call it as a scalar multiplication. So that is defined in this way. So in the case of module, if we denote M to be the given set, and R is any ring, we have to consider R, small r from capital R, and an M from this, so that Rm will again it should again be a member of capital M. So likewise here we need to have f of x from fx. From fx we are having this, and from V we have this. So the resultant should again be a member of capital V. So but we are not familiar with this, but we are familiar with the image of V under f of t. T is a member of A of V, already we have mentioned. So when we consider a function of t, again its domain and codomain should be from V to V, and it will be a linear transmission. So the image of V under f of t, because our t belongs to A of V, should be a member of capital V. So in this nice way, the scalar multiplication to make V as an fx module we are having. Now having got this operation, we know already that V under plus is an abelian group. So in order to make this to be an fx module, we need to check the three axioms M1, M2 and M3. So that is, in the case of modules, we would have checked like this. R, if you consider two element M and M prime, this is what we need to show. Rm plus Rm prime, R into M plus M prime is Rm plus Rm prime, and R plus S M is equal to Rm plus Sm, and then we have to show that R into Sm is Rsm. They may look like distributive laws, these two, but they are not distributive laws, because for distributive laws all the members should be from the same set. Here the small r is from capital R, and these are from capital M. These are the axioms we know from module definition M1, M2 and M3. So here in the place of r, we have f of x, and two members are to be taken from capital V. So we have this, and what we need to prove is this as m1. So when you consider the left hand side, f of x into u plus v, by this definition it should be the image of u plus v under f of t, and because f of t, it is mapping by the it is a linear transformation, it's a homomorphism, so we have this step. So this is because f of t is a homomorphism, so you have this step, and from here u f of t means that is the image of u, and f of t means by this definition it is f of x u, and in the same way the next one, and that is what we need. So we have got our right hand side of m1. Now in m2, similar to this, we have to have f of x plus g of x into v is equal to f of x into v plus g of x into v. So we consider the left hand side, and that is nothing but the image of v under f of t plus g of t. So here this step comes because if that is how your addition is defined by the definition of addition in a of v. By the definition of addition in a of v, we have this step, and again from here addition in a of v, using addition in a of v, this step comes, and this is by this definition we have this step. So that gives your right hand side of m2. And then to prove m3, so here r into sm, so f g of x into f of x v. If we consider this, then we have to show that this is g of x into f of x v. So we shall consider RHS here first, and this is nothing but by this definition the image of v under this composition g of t composition f of t, and whether I consider g of t composition f of t or f of t composition g of t, it is the same, because the transformation, the same transformation is only used. If we have two different transformation s and t, then s composition t is not equal to t composition s. But here both of them are involving only t, so this is allowed. And this is v f of t, that is the image of v, and this is by the definition of composition of mappings. By the definition of composition of mappings, this step comes, and this you treat as some say w. Then in that case you have w, the image of w under f of t means it is this. So instead of f of t you have g of t, so g of x w. So if you want in between you can have g of x w, and this w stands for v f of t, and again the image of v under f of t is f of x v. So you get this step. So that is your LHS. So we have made our v, which is already a finite dimensional vector space, to be an fx module. Now because v is finite dimensional vector space, v becomes finitely generated fx module. So we have now two roles being played by our v. One is v is finite dimensional vector space, the other one is v is finitely generated fx module. Now if v is a finite dimensional vector space, then we have this v to be the direct sum of v1, v2 and so on vk. This is the decomposition theorem which is proved in the case of in the section Jordan form, Jordan canonical form. So there we have established this v is the direct sum of v1 etc vk, where vi, there of course we defined our vi to be all those vectors which are annihilated by q of t power some li. So like this we defined there our vi's to be, and they are all invariant subspaces, but when we regard this as fx module, they are considered as cyclic submodule. They are considered as a cyclic submodule because fx is a Euclidean ring. So fundamental theorem on finitely generated fx module if you use this, then you have your V being written in this way, each Vi is cyclic submodule. But when we regard our V as finite dimensional vector space, we have also proved the same thing. So in that case, Vi's are described in this way, kernel of, okay, this transformation. Like that we have in the case of Jordan canonical form that is established. So throughout this section, it has to be remembered that our V plays both the roles. It's a finite dimensional vector space as well as it is an finitely generated fx module. It plays both the role. So depending on the context, we may be using this and this, or in some cases both together we'll be using. Now we say that V is cyclic relative to T if for every W in V there exists V in capital V such that W is the image of V under f of T. Now this is somewhat similar to our cyclic module, which already being defined in Herstein in section 4.5, cyclic module. See, we say that M, the given M to be cyclic module generated by M naught whenever any small m in capital M is written as M is equal to R into M naught, where R is a member of capital R. Capital M is, you have that to be an R module, and that we call as cyclic module whenever you have this. This is similar to your definition of cyclic group. So in this case also, when we have this V, we can say that V is generated by this small v. Or we can say, we can whenever I consider any element, say W in V, if I am able to write my W as f of x v, in the place of R I have f of x, so f of x v. But we know already that this f of x v is Vf of t, so that W is written as Vf of t, the image of V under f of t. So in that way we can remember that V is said to be cyclic relative to t whenever we have W being written as Vf of t. If for every W there exists one V in V such that. So this definition will be used in the next lemma, which states that if V is cyclic related to t in A of V and P of x is this polynomial, P of x is this polynomial, then M of t is given by, what is M of t? That is, I am given V to be cyclic relative to t, and the P of x is given by this. It is the minimal polynomial of t. Then what we need to prove is there exists a basis of A in which the matrix of t takes this particular form. So we have to have the definition of cyclic module that needs to be used here, and even in this case we will make use of, said earlier, V is both fx module as well as it is a finite dimensional vector space. Right, so we are given V to be cyclic with respect to t. So by the definition we have W is equal to the image of V under f of t, that is W is Vf of t, where t is a member of A of V. We shall call this as equation 1. Now this P of x, we will consider the minimal polynomial of t. So it is the polynomial satisfied by t of least degree. So P of t should be zero transformation. So we have this. So from here we need to have, this is gamma naught I. Then the rest are with the transformation. Even this must be provided with transformation. So it is minus gamma naught identity transformation minus gamma 1 t and so on minus gamma r minus 1 t power r minus 1. So this we shall name as equation 2. Now we claim that if at some polynomial s of x in fx, the image of V under S of t is 0, then S of t itself should be 0 transformation. That is, S of t should be identically 0. For this reason, see, you consider your the image of W under S of t, but W stands for V f of t, the image of V under f of t. So we have this step, and we can rewrite this as V f of t S of t. So that is what we have here. And again, as said here, composition, it is between the same transformation only, so we can interchange these two. So we get this step, we can interchange these two, so we get this. And again, compositional mapping definition, so you have this by this one, that is V S of t 0. So we are making use of this over here, so you are getting 0 f of t. So this is vector 0, this is vector 0, and this is transformation. We know that a transformation always takes vector 0 to vector 0. So we have proved that W S of t is equal to 0, and this is vector 0. We can rewrite this as W 0 transformation, because 0 transformation will take any vector to vector 0. And so because the images are equal, the mappings must be equal. So S of t should be 0, identically 0. So we see that whenever we have a polynomial S of x in fx with the property that V S of t is 0, then S of t itself should be 0. So this we will be using in proving that given a set of vectors, we are going to consider them, and they are linearly independent. To prove that, this is going to be used. Now we will consider Vt square and so on, Vt power r minus 1. We will prove that they are linearly independent. Suppose they are not linearly independent. Assume the contrary and arrive at a contradiction. So it is method of contradiction that is used to prove this. So suppose you consider the linear combination of these vectors equate to the identity element, which is 0 here in V. So we consider this where all of the scalars are 0. So linearly independent is our claim. So we presume that they are linearly dependent, which means there exist scalars not all 0 such that the linear combination is 0. Then from here we have this step because it is transformation, and how addition is defined in A of V. Using that, by the definition of addition in A of V, this step comes. And suppose I name this as, say, g of t, that is g of x stands for this polynomial, then this would represent g of t. This one will represent g of t. G of x is taken as this, means this is what we get. And just now we proved that the image of V under g of t 0 means g of t itself should be 0. Now what is the degree of g of x? Its degree is r minus 1. We have already taken p of x, which is of degree r, to be minimal polynomial satisfied by t. So but here you are getting g of x to be a polynomial of degree r minus 1, which is less than the degree of the minimal polynomial with g of t 0. So which is not possible because g of x degree is less than the degree of the minimal polynomial p of x. So what we conclude is these are linearly independent. Also from equation 2, we can write our t power r minus k as a linear combination of 1, t and so on, t power r minus 1 where k is greater than or equal to 0. So because of that, when we consider any w, see next is that these span our v, we'll have to say. So we have we consider this one w, which is known already as image of v under f of t. So that v is a linear combination of 1, t, because whatever may be the polynomial, its degree it will come down to this one, that is t power r maximum degree, we can have it as r minus 1, for the reason that whenever you consider t power r minus k, it will be again a linear combination of all this. So whatever may be the degree, see for example, I have my r to be say 3, then I will have 1 t square. So if I have t cube, already from here, see already from here, if I consider p of x, gamma naught plus gamma 1x plus gamma 2 x square plus gamma 3 x cube. We have taken our r to be, we have taken our r to be 3, so this is what we get. Gamma, it is gamma 2 x square x cube. Coefficient of highest power should be 1. So from this, because p of t is 0, we get t cube plus gamma 2 t square plus gamma 1 t plus gamma naught I equal to 0, which means t cube will be minus gamma 2 t square minus gamma 1 t minus gamma naught I. So your t cube will be linear combination of 1 t square. Okay. So in the same way, if you have t power 4, then you can have that as t power 4 means we can have it as t composition t cube. So that is again a linear combination of this. It will involve t cube. Again you can make use of this. So ultimately you will have whatever may be the index. You have when you consider degree of p of x to be like this, then you can always write that t cube, t power 4 and so on to be linear combination of just t square. So it is in the same way we have here. And so when you consider v f of t, v as a linear combination of 1 I, it is actually I, t and so on, t power r minus 1. So when I consider together with this, it will be a linear combination of v, vt and so on, vt power r minus 1. So these span v. Already they are linearly independent in V, and these span V, so they form a basis of capital V. Now we consider V1t. See, our aim is to find a basis. We have got a basis, and then we need to find what is the matrix of T in that basis. So for which we need to have such a representation. So V1t here, V1 is, this is only for convenience sake that we are writing. Choose this as your V1, V2, rewrite, and this as VR. So V1 to VR that we have, V1 stands for V, so VT you have, and VT means it is V2, VT means it is V2, so there is no V1, so 0 into V1 we have, and this is 1 into V2, this is 1 into V2 plus and so on, 0 into VR. You don't have VR term. Similarly, V2t, when we consider V2 is VT, so VT t, that is VT square. VT square is your V3. VT square is your V3 here. So 0 into V1 plus 0 into V2 plus 1 into V3 you will have, and so on. So coming to the last one, VRT, when we consider it is Vt power r, V, it is actually Vt power r minus 1 t. So that will be t power r, but again t power r here we have already written t power r as the linear combination of I and so on. So we have I, t square and so on, t power r minus 1. So ultimately we have this to be gamma naught V1, and this is minus gamma naught. This is minus gamma naught V1 minus gamma 1 V2 and so on, minus gamma r minus 1 VR. So the basis, whatever here we have, the same basis in all we have. So now that we can write out our matrix of T in that basis, it will come out to be like this. So this is what we have to establish, and we can easily see that we have this one to be our identity matrix, this one to be our identity matrix, and the order of this is r cross r. Order of this, because your degree of p of x, degree of p of x is r, and this is r cross r matrix, and we have from 1 to r, so it is r cross r matrix. Now we have, we call this matrix to be companion matrix of p of x, and here goes the definition of companion matrix. If f of x is a polynomial whose highest power is 1 as in f of x, then degree, you see, not to know about the order of the matrix. Whenever we are asked to write down the matrix, first question to be asked is what is the order. So here order is determined from the degree of the polynomial. Suppose I have, say, my f of x is, say, x cubed plus 3x square plus 4x minus 7. This is my f of x. I want to write out the companion matrix of this. I look at the order, the degree of this. So then I get the order of the matrix. It is 3 cross 3, and here the constant term should be written first with negative sign. So already here you have negative sign, so it will be 7. And next is the coefficient of the x term, so it is here minus 4, because you have 4 here, but we need to have minus sign, so you have minus 4, and here you have minus, so you have minus 4, and the next one is 3x square. So here had we written that here minus alpha 2, so that in this case minus 3. So 7 minus 4, 3, and the super diagonal entries should be main diagonal, this is super diagonal. So you have, this is main diagonal, and super diagonal should be 1. So this is what our companion matrix of this particular polynomial. Given the polynomial, we can write the companion matrix of that polynomial, and this is what we have, 3 cross 3 matrix. So in view of the above definition, the above lemma can be restated as if V is cyclic relative to T, and if the minimal polynomial of T in fx is P of x, then in some basis of V, the matrix of T is the companion matrix of P of x. So that will be used. That lemma will be used to prove the next proposition. This is used in the case of this theorem. So that is used, and in between this is an important proposition which states that it's a nice proposition. The characteristic polynomial of the companion matrix C of P of x is P of x itself. The characteristic, see, if I am given a polynomial, say P of x, suppose I am given a polynomial, say P of x, okay, then for this polynomial I can find out companion matrix. Now given any matrix, we know how to find this matrix is matrix A if I denote. We know how to find the characteristic polynomial for this. For this we know how to find the characteristic polynomial. So it will be again a polynomial of some degree, generally speaking. See, if I have the order of this to be, say, r cross r, means polynomial of degree r I will get. If this is of degree n cross n, I will get again this to be a polynomial of degree n. So if degree of P of x is, say, n, the companion matrix of this polynomial will be of order n cross n. If this matrix is of order n cross n, the characteristic polynomial will be of degree n. So what we are trying to prove in this is ultimately you will get this to be P of x itself. So we consider a P of x, a polynomial, for which you find the companion matrix. Being a matrix, you can find the characteristic polynomial, and that characteristic polynomial is nothing but the polynomial you consider at the beginning. So this is what we are trying to prove. So first you consider p of x. This, let p of x be what is given to us, that we will consider. So once this is given, we know how to write the companion matrix of this. Having got a matrix A, we know that how to find the characteristic equation. So characteristic polynomial, so this will give the characteristic polynomial, whether you consider determinant a minus xi are equal to 0 when we put characteristic equation, you get this. So we consider here determinant xi minus a, that is a is nothing but this. This is what we get. Now we are going to use the elementary properties of determinants to further simplify this. So what are the property that we use? We are going to add to the first column x times the second column, x squared times the third column, etc. So we are adding this. If you want to check, you can try with some 3 cross 3 matrix, so that all these explanations can be clearly understood. So what we do is this: by adding to the first column, x times the second column, x times this second column to this is the first column, to this we are going to add x times the second column and x squared times the third column, and so on. And then x power r minus 1 times the last column, this one, x power r minus 1 the last column. So that we are going to add to the first column. So when we do that, we get an expression like this. So here when we expand this out, we get p of x. So ultimately you will have minus 1 0 0 x minus 1 0 0 and so on. This is what we get, and this is nothing but we can try this. See, actually suppose I have, say, p of x second order we shall consider, so that p of x is, say, x square plus, say, some 2x plus 3. So what will be companion matrix of this? It should be 2 cross 2 matrix. It should be 2 cross 2 matrix. So you have your minus 3 here, minus 2 here, and then 0 1. So this is companion matrix. We want to find this one, determinant a minus xi or xi minus, that doesn't matter. We are going to consider with some minus 1 power that we will get, so that doesn't matter. So we have we shall consider our xi minus a. So it will be x minus 1 3, and then this one will be x plus 2. When you expand this, you get x into x plus 2 minus 3. So you get x square plus 2x. This is 3 into minus 3, so plus 3. So this. So we started with p of x, and we have got the characteristic polynomial. This is Cp, characteristic polynomial of this matrix. So we have got again the same. Okay, now coming to this one, when we consider this, we are asked to add to the first column x times the second column. So when we consider this, we computed for, because it is second order matrix, directly we were able to compute, but our aim is to illustrate what is given in wordings here for general case. So to the first column, add x times of the second. So that means you have minus x, 3 is already here, so x times the first one, so you get x square plus 2x. Okay, this one will remain as such, x plus 2, this is what we get. So that means here you get 0, minus 1, 2x plus x square plus 3. 2x plus x square plus 3 is nothing but your p of x. And this one is retained as such, x plus 2. So the same thing, gamma r minus 1, you have, so you have your the xi minus c p of x being given by this way, and when you take this out, we are going to expand this, so p of x into, you are going to delete this column and this row, so minus 1 that you will have, minus 1, and in this case again a simpler one we have considered, so we have got only this, so it will be actually when you expand it, this is plus, this is minus, means you will have one more minus sign. Okay, so you will ultimately arrive at p of x. So it is these kind of operations when you perform, ultimately you will arrive at this. And so the characteristic polynomial of the companion matrix of p of x is p of x itself. Now comes the second, the main theorem is this, and for which we need to establish this theorem. That will be done in the next video.